Welcome to the Explainer. Let's just dive right into this. Today, we're unpacking what is easily the most unforgiving architectural hurdle in all of distributed systems: consistency and consensus. If you're building data-intensive applications at scale, getting a grip on the mathematical realities of how nodes coordinate, well, it isn't just a nice-to-have. It's literally the difference between a rock-solid, resilient architecture and one that silently corrupts your data.
So, why is agreeing on the truth the absolute hardest problem in computer science? Let's establish the stakes right up front. In a distributed system, your nodes share zero memory. There's no global variable they can quickly check, no shared absolute physical clock. Instead, they rely entirely on chaotic, completely unpredictable networks to talk to each other. Truth isn't something a node can just intuitively know. It has to be rigorously mathematically negotiated.
Here's our roadmap for the breakdown today. We'll start with the distributed coordination problem, move through the mathematical illusion of linearizability and its true costs, explore causality and partial ordering, unpack the math of reaching distributed consensus, and finally, bring it all together into a final architectural view. Okay, let's get moving. Starting with Part 1, the distributed coordination problem. Let's look at the physical limits of our networks. If we sketch this out, we run right into a fundamental physical constraint of our universe, the zone of uncertainty. Picture an observer node sending a request to a remote peer. Now, imagine it doesn't get response. That node is now stuck in the zone of uncertainty. Why? Because it literally cannot mathematically distinguish between a remote peer that has completely crashed and a packet that was just dropped or delayed by the network. Because of this baked-in uncertainty, no major decision in a distributed system can ever be made safely by a single node alone. It's just too risky. Moving to Part 2, the illusion of linearizability. This is what we wish our databases could do.
Let's define the absolute gold standard of consistency models: linearizability. It's a recency guarantee that makes the entire system appear as if there is only a single copy of the data and every single operation is perfectly atomic. Think of it as the single copy illusion. The second a write completes, every subsequent read across the entire distributed system must immediately see that newly written value. It behaves exactly how we expect a single local CPU core to work.
But here's where physical reality totally breaks that illusion. Let's trace this out on a timeline. Say a sports match result is written to the leader node. Germany scores. The leader immediately starts replicating this. Alice reads from a follower that got the update fast, so she sees Germany won. Awesome. But Bob, querying just a microsecond later, hits a different follower that's experiencing a slight replication delay. He reads a stale score of 0-0, so Bob hears Alice cheering, checks his phone, and sees a game that hasn't even finished yet. The single copy illusion has totally failed us here. We've just hit a causality violation.
Which brings us to Part 3, the true cost of consistency. Let's confront the harsh realities of physics and the CAP theorem.
Achieving strict linearizability mathematically forces our hand. During a network partition, say when two data centers completely lose connection, you have to make a choice. You either remain perfectly consistent but become completely unavailable, just throwing errors back to your clients, or you stay available but drop linearizability, risking stale data. But get this, even when the network is perfectly healthy, linearizability is fundamentally slow. As researchers Atiyah and Welch proved mathematically, linearizable response times are strictly proportional to the uncertainty of delays in the network. Every single linearizable read or write demands heavy, expensive coordination.
Let's look at a practical alternative in Part 4, causality and partial ordering.
The key here is understanding the stark difference between a total order and a partial order. Linearizability demands a total order. It's like integers. Every single operation in the entire system has to be definitively ranked in one massive single global timeline. As you can imagine, that creates a huge global bottleneck. Causality, on the other hand, relies on a partial order. It acts much more like mathematical sets. If two events are concurrent and completely unrelated, we don't force them into a strict, arbitrary queue. We just let them remain incomparable.
Let's map out this branching timeline. This setup illustrates exactly why causal consistency is such a pragmatic compromise. It preserves what we call the happens before relationship. If operation A actually caused operation B, the system absolutely guarantees B is never seen before A. But for concurrent operations, they can just branch out and merge later on without needing heavy, system-wide synchronization. It's a game changer. It's the strongest possible consistency model that won't get bogged down by network delays, and it remains perfectly available even during partitions.
Now, to actually track this causality, we have to completely throw away the concept of physical time. Time-of-day clocks drift. NTP synchronizations can literally force a server's clock to jump backwards, which causes silent, unrecoverable data loss in last-right-win scenarios. You definitely don't want that. Instead, distributed systems rely on logical clocks, which are essentially just monotonically increasing sequence numbers and version vectors to explicitly map out dependency graphs. This completely untethers us from the messy unreliability of physical clocks.
On to Part 5, Reaching Distributed Consensus. Let's get into the heavy-duty math of agreement.
When nodes absolutely must agree on a single truth, like picking a new leader, we need consensus protocols like Raft or Paxos. True consensus is defined by 3 strict, non-negotiable mathematical properties. First is agreement, or safety, meaning all non-faulty nodes decide on the exact same value, no split brain allowed. Second is validity, also a safety property. The system can't just invent a random value. Whatever they agree on must have been actively proposed by a node. And third is termination, which is a liveness property. The system guarantees it will make progress. It won't just stall out forever waiting on a crashed node.
So how do they actually pull this off without stalling? The secret is the power of the quorum. We don't demand 100% agreement because that's mathematically impossible the second a single node dies. Instead, we rely on a strict mathematical majority. Just look at the equation. W plus R is strictly greater than N. If the sum of your write confirmations and your read queries is greater than the total number of nodes, those sets must overlap. That mathematical intersection guarantees you're always reading the freshest data, even if minority failures are happening right next to you.
Now notice the stop the world pause here. This is mapping out the garbage collection trap. Imagine node B is the leader, but suddenly suffers a massive garbage collection pause. The rest of the cluster assumes it died and safely elects node A as the new leader. But later, node B wakes up. It's now a zombie leader and it tries to write data, threatening total corruption. A split brain scenario. To stop this cold, consensus services attach a monotonically increasing fencing token to every single election. When our zombie leader tries to push a write using its old, outdated token, the storage engine does the math and immediately rejects it.
This whole scenario reveals the ultimate tension at the heart of distributed systems: safety versus liveness. Safety simply means nothing bad happens. We never corrupt our data. Liveness means something good eventually happens. The system actually responds to the client. The fundamental, ironclad rule of consensus algorithms is that they will happily, intentionally sacrifice liveness, literally halting the entire system just to preserve safety during chaotic network partitions. Data integrity always wins. Finally, Part 6, the final architectural view. Let's pull everything together.
Stepping back to look at the whole system, this is the ultimate paradigm shift for a system architect. Because nodes possess literally zero shared memory, truth is not some absolute physical property just waiting to be discovered. Truth is defined entirely by the quorum majority. A single node cannot know anything alone. Whether a transaction is actually committed or whether a peer is considered dead is simply a matter of what the majority of the quorum mathematically agrees upon.
To summarize our system design, the single-node illusion of linearizability is mathematically expensive, but absolutely necessary for critical bottlenecks like leader election. For general, massive scale, causal consistency mapped with logical clocks is far superior to relying on absolute physical time. And the biggest takeaway, reliable distributed systems don't hide physical network faults behind leaky fake abstractions. They anticipate those failures from day one using the structural math of consensus quorums and fencing tokens.
Which leaves us with this one unavoidable reality. Someday, packets are going to drop. Switches are going to restart. Your network will fail. The math is already written. The only question is your architecture actually ready to handle the truth? Thanks for diving into this explainer with me today. See you next time.